So we want to guess the height by using something, right? So using Euler's method, we can find some height. But you can see the error, right? So to avoid error or to minimize the error, people tried many things, and people found a method like this. If we use just one slope, like this one, then our estimation of the next height is not correct, right? The error is large. But if we use just not just one slope, but different slopes, such as this kind of slope or this kind of slope, we may have a better result, right? This is our hope. So what Rangakara did was using these kinds of intermediate heights to determine the better point than this one, right? So what Rangakara did was determining this kind of height, not by just one slope, but by possibly 4 different heights, 4 different slopes. So this is the idea of Rangakara method. And last time I, in fact, even programmed these things. So we can find this kind of slope and this kind of slopes, and then using average sum, right? So using average sum. So in this sense, we need the copy of this thing and then copy of this thing. So we add these 6 different slopes, right? We add these 6 different slopes and divide by 6 to get the average height, right? Average slope. So we get the average slope like this one. So this is the goal of RK4, and if you have any questions about RK4, ask me.
It takes the 2 inner of your 4 slopes, the 2
inner, right? 2, yeah, right. So exact pattern is having one slope at this point, right? One slope at this point, and one slope at this point, right? So we have 2 boundary slopes, and then at the center we have 2 different slopes. We have 2 different slopes. So we have 2 different slopes at the center portion, and then we have 2 different slopes, and by combining these things we can guess the slope and find the next point. So this is RK4. And as I showed you, it's not very difficult to implement these things. But this is very nice method because the error is not very large. Error is not very large. So under this assumption, today we will cover 2-dimensional differential equation, or generally n-dimensional differential equation, and then higher order differential equation. So there are 3 cases we can cover using RK4. So 2-dimensional differential equation is given in this pattern. Y prime equals a function of independent variable x, and then y, and then z, and then z is given by the function of independent variable x, y, and z. So y and z derivatives are given in this pattern. Then it's 2-dimensional differential equation. So generally we say, oh, this part is called f of x, y, z, and this is called g of x, y, z. Then we want to find some function, some vector satisfying these things. So we want to find some vector satisfying the above differential equations. So how can you do it is the next task. And it is essentially identical. It is essentially identical. What should we do? We find the y slope, right? We find the y slope, and then z slope at the beginning point, right? We find y slope at the beginning point, and then z slope at the beginning point for, say, x0, right? So we find y slope and z slope at x0. And then we advance to the middle portion, right? We want to find the slope at this point, right? We want to find the slope at x1. This is our goal. There are two different graphs involved here. Then we want to find the slope at this point, but we don't know, so we just use some possible slope, right? But it's not the order we do it. We initially use this slope to find something, and using this at the center, at the middle point, we find another slope, right? We find another slope. And then using this, we find another slope, and then we find this slope using these things. And similarly, z slope can be determined a similar way. So we find slopes of y and z. So essentially, the same thing as first order. The only difference is using these two variables, y and z. So instead of writing down the formula, I will show you the direction. So this is the part you can use. What I used instead of y and z, I used x and y with independent variable t. So it's the same. Only difference is using different letters. So this is the formula that we can use. So initially, the differential equation is given in this pattern. We have an independent variable, t everywhere, and then dependent variable x and y. Instead of y and z, x and y are used in the formula. And initial conditions are given. Initial starting point is given. t0, x0 is t0 in some sense. Then we find the first slope. Right? So we should program in this order. You should find K1 first, right? K1 first, and then L1, and then K2, and then L2. So we should program in this order. You should not program K1 first and then L1, because as you can see in the formula, we need L1 information, L2 information, right? So L1 information is obtained by calculating L1 here. So we should program this way. So essentially the same as first order case, but both x and y are used, or y and z are used, we should program in this order. And then essentially, formula is the same. So RK4 with 2 dimension is very important because it handles higher order equations too. Any questions about two-dimensional case? Then this is the situation. As t varies, both x of t and then y of t varies, right? So as t varies, x of t varies, and y of t varies. So we can individually calculate x of t and then y of t to solve the differential equation. Any questions? And nth order differential equation is not very different. Assume that we have this situation. X of 1 is not a good idea to use subscript that way. So I will use x, y, z. X prime equals some function of t, x, y, z. Y prime is a function of t, x, y, z. And then z prime. So we have three different slopes, right? Three different slopes given. Then what should we do? Almost the same. Almost the same. We must attach one more. We must attach one more column. We should attach one more column, right? K column, L column, and then M column, right? Say M column. We should attach M column determining the slope of z. Do you follow me? And if we have one more letter, I will describe the situation. To do it, to solve this, we should use K1 column, K2 column, and so, right? K3, K4, and then L1, L2, L3, L4 should be determined to solve second order case. But now to solve this case, we should attach M column representing the slope of z. Right? So we should determine K using similar formula to this one, using similar formula to this one. And then we should determine L using similar formula to this one, and then M using similar formula to this one. Do you follow me or not? If you don't, then I will slow down, but if you completely understand, then I can continue.
Scroll back up to the
Formula.
yeah.
So we have formula like this, right? K formula like this, L formula like this. Almost essentially the same, right? So we attach one more variable, so comma and one more variable, and then attach the similar. If you don't understand, ask, then I will write the M1. Yes?
So what are the differences between x of t and y of t? Like, one of them is the function height.
So it's like this. It's like this. As time varies, we want to determine the position, right? We want to determine the position as time varies. So in one-dimensional function case, as time varies, the height can be represented by just one graph, right? But now, as time varies, both x and y varies, right? So we usually use time variable in this direction, and then x in this direction, and then y in this direction. Then as time varies, both x and y varies, and then it's a curve in the space. So we want to find the curve in space. That's the difference. So if we look at just x, then if we consider the projection of distance, then it may look like this, right? If we consider the projection of y in t, then we may see this kind of curve, right? Projection. And then we see the projection of this. Yeah, so it is the space curve.
So that's the projection on that.
Right, onto x-axis or y-axis, but if we don't project, then it is the curve, the two-dimensional curve, right? But because of time change, we think, because if we frame it, then at each time it is at one position on the plane. But time change, time itself becomes one axis, so it's like three-dimensional curve, right? It looks like a three-dimensional curve. But if we don't consider time frame, time axis, if we remove time axis, then what we can do is pinpointing position. So I will show you the case, because in three-dimensional case we need it. So I will just write one more case. Assume that we don't add time axis. In other words, just x-axis and y-axis. Assume that this is the case, then what we can do is this one. At time 0, the point was here, right? At time 1, the point is here, right? At time 2, point is here. At time 3, point is here. At time 4, point is here. So we can in fact sketch all these things in plane. But this doesn't have time information unless we specify time information in each point, right? So this point is time 0 point. And then this point is time 1 point, time 2 point, and so, right? Time 3 point. So it's two-dimensional, say two-dimensional curve in reality. But because of the time axis, it looks like three-dimensional curve. But as you can see, as time changes, it moves in the two-dimensional space. Then assume that we add one more axis. In other words, x-axis, y-axis, and then z-axis, three-dimensional, right? And the time changes, then we can pinpoint the time. Time 0 is here, time 1 is here, and then time 2 is here, and so on, right? So we can sketch the three-dimensional curve. But we should specify time. So it's three-dimensional movement, right? This differential equation gives us the movement of a particle in 3 dimensions, right? In this 3 dimension. So movement of particle is represented by this one in 3-dimensional space. Then what does this mean? This means if we consider the projection of the curve on the x-axis, right? If we consider the projection of this curve on this x-axis, okay? Projection, then what is the slope? Stuff like that, right? Or above the, not on, but above the x-axis, then what is going on? Y-axis also. Right, slope or speed. Because we use time, speed might be good. So speed in x direction, speed in y direction, speed in z direction might be better than slope. Because once we use both dependent and independent variables together like this, then it is the slope, right? But in this case, we don't have this kind of independent axis anymore. If we don't have independent axis anymore, then all we can do is just move, describing the movement. So take a look. Assume that we sketch the one-dimensional curve here using just time represented time 1, time 0, time 1, time 2. Then all you can describe is movement, right? Then instead of slope concept, speed concept might be better. Do you follow me? So if we use this kind of graph, it represents slope. The derivative represents slope. But if we use this kind of concept, then the derivative represents the speed in the x-axis. Do you follow me? So the same thing, but explained differently. X prime in this kind of graph represent the slope of this curve, right? X prime represents the slope of the curve. Right? This is X prime. If we use both independent and dependent thing together. But if we don't write this thing, only x-axis is given and then time is specified, then where is slope? Then the speed of or velocity of the particle, right? Velocity or speed of the particle is represented by the derivative. So rigorous term is velocity, right? Rigorous term is velocity in x direction. So this represents velocity in x direction, and then this represents velocity in x direction and y direction, right? In 2 dimensions. Velocity in x direction and y direction, and this represents velocity in x, y, z direction. Velocity is in x, y, z. So we covered the method and mentioned we are not in this course. We are not very interested in learning about the differential equations themselves, because these kind of things are covered in other courses. In this course, we don't care. Assume that these things are given. We don't have to know about the background of these things. Just assume that this is given, then how can you solve it? This is our concern. And the case can be solved by doing this kind of stuff with one more column, right? So I will write one example in three-dimensional case. So K1 should be equal to what? K1 should be equal to, if we follow the same notation, H times f of T n xn yn and then zn. So this is all you need to know, right? This is all you need to know. Where f is given here, right? F is a function of t, x, y, and then z. Similarly, y is g of t, x, y, and z, and then h of t, x, y, z. Right? So these are all given by the problem. You don't have to worry about f or g or h. These are all given by the problem. Then L1 can be rewritten. L1 equals h times g of what? Tn, xn, yn, and then zn. And then similarly, m1 is equal to what? Can you guess m1? H of I used H, so I will say H is confusing, so I will use different letter. What letter do you recommend? Let's use P. Let's use P function here. Then P of Tn, Xn, Yn, and then Zn. So you can guess columns, right? Assume that we have more variables. In other words, instead of just three-dimensional function, assume that we have four-dimensional function. Four-dimensional function doesn't appear in usual space, but when you consider financial problems use not just 3 factors. It may use 5 factors or 6 factors, right? Financial problems. So we may consider the factor of, for instance, oil price, right? Something, then we can add all these things together to solve something. So in this case, I showed you the possible column. K looks like this, L looks like this, and M looks like this, and you can just gather the other rows, right? I just showed you first row. Assume that we have 4 variables here instead of 3, then we must add one more column here, right? And one more column here, and then you can add as many columns as you want. So technically, it's not very difficult. Do you follow me? Great.
So when calculating K2, it's going to be whatever Tn plus h over 2. Is it also going to be xn plus l over 2 and yn plus m over 2?
You mean these things?
Yeah.
As you can see, K1 is a number, right? You are correct, right? So yeah, so you are correct. So we calculate these stuffs, then these stuffs multiply by 1/2 or 0.5, right?
And then we use the 1/2 of each one.
Right. These kind of things are all used. The same. Exactly the same. You can once you write, you will know that all these are used downstairs, right? First row is used in the second row is in the third row, and so on.
Okay, cool.
So I only wrote down the first row, but second row can be used. So we can handle the differential equation having n independent variables, right? N independent variables. I mean dependent, what I meant was dependent. Only one independent variable called t, right? Time, but dependent. So differential equation, n-dimensional case used. Now the final thing is higher order differential equations are about I guess 4 years ago, some professor in engineering came to me and asked about the method of solving this kind of differential equation. So I said there is nothing straightforward. There is nothing straightforward to solve second order differential equation. Nothing.
Coefficients, constants, or functions?
Anything can come, right? Anything can come here, right? Or if you divide everything by p, then q over p, r over p, right? And then we can call q over p another q, and then so we can say just one. Then how can you solve this kind of second order differential equation? There is no straightforward method to solve this one, but using the n-dimensional case, we can solve it. How? We write it by using two variables, right? So we call y of t equal to y1 of t, and then we call y primed of t equal to y2 of t. This is the idea. So we introduce two dependent variable like x, y, z, right? We used x, y, z stuff. So we introduced two dependent variables. And then write the differential equation. How? y1 derivative is equal to y derivative. And by this definition, y derivative is what? y2. Right? Y derivative is y2. Similarly, y2 derivative is y derivative, and then y second derivative. Because of the top equality, y second derivative is what? Y second derivative is minus r of t y minus q of t y primed of t, right? By the top line. So we write this part using the top line minus r of y minus q of y primed, or we can use y1 and y2. If we use y1 and y2, what is this? Y is what? y1. And then y primed is what? y2. So we can create n-dimensional, two-dimensional differential equation. But what is the difference? In this case, the order of the differential equation is not 2. The order of the differential equation is 1, right? This is the first order n-dimensional differential equation instead of one-dimensional second order differential equation. So one-dimensional second order differential equation cannot be solved. One-dimensional second order cannot be solved, but two-dimensional first order can be solved by using the technique that we learned. So please check these things and ask questions. Then by using RK4 with two-dimensional, right? Two-dimensional RK4, you can solve this. Then you don't need both. You need just Y1 information. You have found the information of, so I will sketch it in this plane. Once you solve, you will solve for Y1 and Y2. Do you follow me? You will solve this for Y1 and Y2. So as time changes, it will move. Right? You know the speed in Y1 direction, and you know the speed in Y2 direction, right? So this could be the curve, right? Time equal to 0, time equal to 1, time equal to 3, and so on. So we can have time changing here, and then Y1 change Y2 speed.
What is the system that we're solving here?
So I will write the system here. y1 prime equals y2, and then y2 prime equals minus ry1 minus qy2. So this is the system. So two-dimensional first order system is created. Then by using the two-dimensional RK4, you can determine this kind of thing. As time changes, right? As time changes, y1 and y2 changes, right? We know the speed, and then we can sketch the movement. Then, this movement is not very important. The important thing is not this movement. The important thing is movement in the y direction, right? Moving this kind of thing, right? So this kind of thing is the important. But as you can see, because we remove the time direction, we don't know what is happening, right? Only we describe point movement. So to look at that kind of movement, we may introduce time direction and then sketch these things. Then we can consider the slope to look at the movement. But if we don't introduce time, then this is okay. Actually, we don't see time axis. In physics, can you see time axis? We sometimes represent time axis, but we cannot see time axis. We cannot see time axis. We can see only x-axis and y-axis. And then as time changes, something moves, right? But if we want to capture that kind of movement, we add artificially time, and then time axis, and then sketch these things in this three-dimensional thing. Then we can track down the movement in the direction y1 in the direction y2.
When we solve that system, we're solving for
y1 and y2.
I1 and Y2,
Right.
which are both for each functions of time.
Right. Each functions of time, and then we solve like. So let's return back to z situation or x y situation. You had this kind of differential equation: x primed equals something, y primed equals something. You had this kind of thing. Then what did you do? You solved this thing by using K1 and then L1 column, right? K1, K2, K3, K4 here, right? And then L1, L2, L3, L4. And then you remember the formula, right? So you solve these things, and then you determine the first position x0 given by the problem x1, x2, and so on, right? All these points are determined, right? Similarly, y1, y0, y0, y1, y2, and yn are determined. Similarly, if we solve this case, then we determine y10, y11, y12, y13, and so on, right? So y1n is determined. Similarly, y20, y21, y22, y23, and then y2n are determined. So these points are determined. So y10 is the initial point, y20 is the initial point. So it's like this: y1 axis, y2 axis, right? Then y10, y20 is determined, right? This is the y10, y20. And then next point is y11, y21. And the next point here is, then it looks like this. It moves like this, right? Okay, so you can determine this. So this pair is sketched here. So this pair is sketched here. and then this pair is sketched here, and so, right? So you can sketch the pairs to represent the solution. And knowing these things is very important, because when you handle partial differential equations, sometimes we add independent x's, sometimes we remove independent x's. So you now clearly see the similarity and difference. The clear similarity is this one. If we add the independent axis to the dependent axis, then we can find the slopes, right? We can find the slopes at specific time, right? At specific time. But assume that we just represent the dependent axis and do not represent independent axis, such as time. Then only thing that you can do is moving around here, right? Moving around this. I intentionally use different thing, but it should be all on top of this line, right? This kind of thing should be on top of this line. For explanation, I used a little bit of the stuff here, right? But now you should go here. So sometimes we attach independent axis, sometimes we don't attach independent axis. In reality, this is the actual movement, right? In reality, in this direction, it moves this kind of, in reality. But if we say this thing, then how can you know how it moved? Because of this reason, to capture the movement, we attach artificial independent axis to capture the movement. Then we find the slope and stuff, right? Slope represents speed. So we have faster moving particle here. We have slower moving, faster moving, and then faster moving, right? So we can find movement by capturing it. So you can see the similarity and difference, right? In this case, at least we know how it moves, but we cannot capture it. But in this case, we could capture. But instead, because of this, you may be misled. Oh, y of t, so let's say x of t here and then t. You may say, oh, x of t looks like this. But in reality, no, x of t is not like the curve. X of t is just movement of a particle in the direction x. So if you really look at it, like video, then all you see is just movement of particle in x direction, right? So in fact, what you learned in high school or middle school is all imaginary. This might be the reason why it's so tough. You learn imaginary stuff. But this is the real movement, right? This is the real movement. This is the imaginary movement by attaching independence. And this thing is very important in PDE. So in PDE, sometimes we intentionally attach independent axis to capture the movement. But it's not real movement. So if we detach it, the actual movement is represented by animation. So we take the snapshot of time 0, 0.1, 0.2, 0.3, and then we animate, and we really see the movement of a particle. Any questions? And if you have difficulties about these things, ask me. If you don't, then I will begin to mention about the most important stuff in ODE, boundary value problem, or toughest stuff in ODE. Any questions? when you have, for instance, two-dimensional differential, second-order differential equation, some conditions can be given. Assume that initial conditions are given. Assume that initial values are given, then, for instance, first of all, what is the initial condition? Something like this, or generally time 0. I will use just 0 to make it easy. Instead of using too many letters, I just use this. So these kind of things are given, then the differential equation is called initial value problem. And this kind of thing can be solved by RK4. So it's not very tough. Another type of condition is boundary value problem. Boundary value problem can be given in this poem, right? And this box can be any number, any number. Then, theoretically, sometimes this kind of thing has a solution, sometimes this kind of thing does not have a solution. There are many stuffs covered in the differential equation course, but this is not a differential equation course. So I don't care whether solution exists or not theoretically. I want to use numerical techniques to solve solution, assuming the solution exists. So we don't care whether solution exists or not. We assume the solution exists, then how can you handle it? So this course is very different from theoretical course. So this kind of thing, for instance, you may pick numbers like, it is 1 and it is 3. So this kind of problem is different from initial value problem. Initial value problem at least start at the same point, right? Two different things start at the same point. But here, one starts at this point, the other one, we don't know what happens to the other, y prime, we don't know what happens. So we will learn about 4 different techniques here. 2 techniques were briefly covered in two cases were covered in numerical analysis. So the other 2, I will spend more time. I will briefly introduce the 2 cases covered in in numerical analysis course, but I won't ask you to really program very much on that kind of problems. The basic idea is enough. So I write down the cases. First case is shooting method. Second case is finite difference method. So these were covered in numerical analysis, but we are interested in 3 and 4. Collocation method. and finite element method. There are 4 methods covered in this course. First of all, I will describe the idea part, right? I will describe the ideas, and then after describing the ideas, I will let you know the details. Shooting method is this one. We are solving a differential equation at the boundary A and B, right? At the boundaries A and B. In other words, we at least know the height, right? We know the height. Initial height is 3. And final height is, initial height is 1, final height is 3. So we at least know the heights, right? We know the heights at 2 points. Then shooting method is this one. Assume that we have initial value problem, say y of A is known, and then y prime of A is also known, right? Also known. Then it's not a boundary problem anymore. It becomes an initial value problem that we can easily handle. Do you follow me? So this is the idea. In this case, we guess this stuff and then shoot, right? We guess this stuff and say, oh, 0.1 is my first guess, and shoot. Then we solve this differential equation and shoot, right? Then we may solve the differential equation and then we may arrive at this kind of result. In other words, if we solve under this condition, then y of b could be minus 2 instead of 3. Do you follow me? So this kind of thing is shooting method. We don't have this information. Because we don't have this information, we guess. And then we shoot. Then with this angle, it goes to this kind of position. Then we think, oh, our angle is too low, right? Our angle is small. In other words, I need to increase the angle. Then what happens? So next time, instead of using 0.1, I use 0.9. And then shoot. Then we may overshoot, right? We may overshoot the target, right? So it could be 5. Y of b could be 5 with this angle. Do you follow me? Then 0.1 is too small, 0.9 is too big, then the correct angle might be in between, right? The correct angle might be in between. So afterwards we use bisection. So what we do is this one. 0.1 is too low, 0.5 is too, 9 is too large, then what about 0.5? This 0.6 is the middle point of these two, right? 0.6 is the middle point, middle number. Is it 0.5? 0.5 is the middle number, sorry. The 0.5 is the middle number of these two. Then what happens? With this angle, we may shoot between these 2 points, right? We may shoot between these 2 points. So we may shoot somewhere, right? We may shoot somewhere. Then 0.5 is still low, right? Then the correct angle might be between 0.5 and 0.9, right? Then we pick the middle point of the two. What is the middle point? 0.7. So we pick 0.7 and then reshoot. Then 0.7 could be too large, right? Then what should we do? It should be between 0.7 and 0.5. So next time we pick middle point of the two, 0.6, and then reshoot. And then 0.6 is too large, then we shoot between 0.6 and 0.5, like 0.55, and so on. So we try to narrow down the correct angle. This is the shooting method, and if you have any questions about it, ask. But the important thing is this one. You should not jump back and forth. In other words, you should not increase 0.6 to 0.7 and then decrease this by 1 and then you don't do anything, right? You should not go back and forth. So it's not completely wrong, but this kind of program is useless if we have a narrower error, right? A smaller error. We want a smaller error, then this kind of thing bounce back and forth. We should go to the smaller and smaller and smaller number at each step, right? It should not bounce back and forth. So you should program this kind of thing using bisection, meaning narrowing the boundary of two possible angles. You should not go back and forth by using fixed number because your accuracy will be very limited. If you use this kind of thing, the accuracy is only 0.1 accuracy, right? But if you use this kind of thing, you can have narrower angle and then get a better result. So this is the idea part, and if you don't have a question, then I will mention about the second method. Any questions? Finite difference method is very different. Finite difference method says we are solving the differential equation from A to B. And then we know the initial height here and the final height. So we know these two heights. Then what you do is this one. We guess the height, right? We guess the height at the evenly divided points, right? So we break this up into n pieces. We break this up into n small pieces. And at each point we assume the height using a wireframe line, right? Wireframe roof, right? Using wireframe roof, we just guess the height initially. And then we collect this height information, right? This height information is collected in a vector. So this height is here, this height is here, and so, right? So we collect height information here, and then find some iteration, and then find a better height. And then using this better height with the same iteration, we continue, right? We continue. We find a better height, and so. So eventually, we will get better heights to solve the differential equation. So this is the finite difference method. Of course, details will be mentioned later. Right now, I'm just explaining the ideas. Do you follow me or not? So how to find this kind of iteration is the major thing in finite difference. And what you do is converting the differential equation into many small equations in small boxes, many small, not differential, but algebraic equations in small boxes. So what you do is this kind of thing. We divided these stuffs into small boxes. So instead of solving just one big differential equation, we solve small algebraic equations in each box. And we solve this system, right? We solve this system to determine the height. So this kind of idea will be explained later, but I mean the details will be explained later. Idea part is already explained right here. But if you have doubts or questions about the idea itself, ask me. Then the third and fourth step idea is very important. Third and fourth step use this kind of idea. Oh, instead of solving a differential equation from scratch, let's begin with basis function. So we pick some basis functions. Basis functions are chosen, right? So phi sub I has, for instance, 200 functions. So we use fixed basis functions, right? 200 fixed functions. Then, using these basis functions, we consider linear combinations, such as oh, C0 phi0 plus C1 phi1 and so on, and then C n phi n. We consider this kind of thing as the solution, right? So we use basis function and determine C0 up to Cn to find the solution. And there are two ways of determining these coefficients. One is using collocation, the other is finite elements. Roughly this is the idea. We determine C0 up to Cn by using the information at, for instance, n plus 1 points. Then it's called collocation. So collocation method uses point information at n plus 1 points. Do you follow me? So we want to determine C0 up to Cn by using point information. Finite element method. Finite element method uses weak form of differential equation. Weak form using integration. How? We have a differential equation such as this one. Or something, right? Then we integrate the function with each basis function. Right? We integrate. Then for each basis function, we have one equality, right? So we have n plus 1 basis function, meaning n plus 1 equation. So depending on the method, sometimes it's called collocation, sometimes it's called finite element. Of course, details will be mentioned later, but idea part is completely explained, and then please browse these 4 ideas to solve boundary value problems. And collocation method looks like power series solution technique. Looks like. It's not really power series, but you may feel that you are solving power series solution problem. Finite elements method is solving a system. Why? This kind of thing is the individual line of the system, right? Individual equation of the system. And as you know, this is the toughest. If it is solving one-dimensional problem, it's not very difficult, right? One-dimensional dependent variable problem, then it's not very difficult. But we are solving two-dimensional one, then it's way tougher. So I explained 4 cases, and then please browse your note or the board and then ask questions, because as I mentioned before, all these four techniques use very different techniques and ideas. You should completely understand what each method means.
When you say weak form, so I went back like this, I'm still not good. Does that just mean it's integrating with the basis function?
Right. So this is a strong form. Right? This is a strong form, right? This is strong form, but we attach something like this, then it becomes weak. In other words, something that is not necessarily satisfying this may satisfy the top one. That kind of thing is called weak form. So in real analysis, how How many of you took real analysis course? In real analysis, we learn these kind of things, right? We learn these kind of things. Sometimes these are equal. Sometimes you can make a counter example. Even though this is valid, this may not be valid, that kind of thing. But this is not a course covering theory part. Just learning about legitimate ideas and techniques to solve differential equations. What else is the question? Collocation, finite element, or shooting, anything. Anything you can question. Important thing is this one. The weak form that we cover, the idea that we cover here, is required in higher order differential equations. PDE problem instead of just ODE, PDE problem. In PDE we have two independent variables, x and y, right? X and y. And then the result surface, right? Or resulting shape, right? So this kind of technique is also used. Then I will mention about shooting method and take a break, and then after break, briefly mention about finite difference method, and then I will spend most of my time on collocation and finite element method. So shooting method is this. Roughly, we have differential equation. We have this kind of differential equation, second order differential equation with boundary conditions. Y of A is given, and then Y of B is given. So let's say Y of A is alpha, and Y of B is beta. So this is the differential equation we want to solve. Then guess the initial shooting angle. So we guess the initial shooting angle, say G. So we guess the initial shooting angle, say G, and then shoot. So we solve G is our initial guess. Initial guess is G. So I used 0 value, but your G can be anything, any number. But as you can see, even this one is a huge task. It is a second order differential equation. Second order differential equation can be directly solved or not. It cannot be directly solved. To solve this one, you should make a system, right? Two-dimensional first order system should be made. And you should solve a system. So even this one, using RK4 itself, is tough. So please check whether you can really solve this or not. So now we are handling a initial value problem, right? Solve the following initial value problem, right? Solve the initial value problem here. we are solving boundary value problem. To solve the boundary value problem, we are solving the initial value problem using RK4. But as you can see, because it's second order differential equation, what we can do is using system, right? Using a system, right? The two-dimensional system, first order two-dimensional system using RK4, and then you solve. Then, in the end, we will find the result, right? Using this, you will find y of b value, right? So say b, capital B is found. If b is lower than beta, right? The target height, right? Target height is beta. Then, what does this mean? Our initial shooting was too low, so we should raise the angle, right? Then, what happens? Now, new G should be found, right? So new G is, for instance, previous G plus some number, such as 1. And then do the same thing. After doing this, we return back to this. And then check whether this happens or not. If this happens, we increase one more. This is the reason why I don't like to use specific number. So I will say G instead of saying 0, right? Instead of saying 0, I will use G. Do you follow me? So we initially shoot and then check whether it's low or high. If it is low, then increase until it becomes high. So once it is out of this, what does this mean? Once it is out of this, what does this mean? It means, once it does not loop anymore, it means B is greater than or equal to beta, right? Do you follow me? Once it is out of this loop, it means our angle, our G is now correct. If you don't follow me, ask me. So what we have done is this thing. We initially guessed 0 angle and then shoot, and then after shooting we got B while beta is here, right? And then we increase this angle by 1, right? And then we reshoot and then find another B. And then we increase this angle and then reshoot, and then at last we arrive at some point where B is greater than beta. If we happen to have B equal to beta, then done, right? Then you have solved the problem. It rarely happens, it is usually above. But it's lucky. Then you can guess two numbers, right? This previous height and this height are enough, right? So the angle should be between this height and this height, right? So you record the previous B and then current B, right? Once it is out of loop, previous B and current B are boundaries. Then afterwards, what should we do? What should we do? We use, so let's say B previous, right? B previous and then B are the two heights that we will use, right? B previous is smaller angle. I will say B previous here. When it's out of loop, right? B previous and B are kept. Then B previous, B are chosen. Then middle height, B middle should be found, right? And then check whether this B middle is above or below. Then it's bisection, right? Afterwards, it is not just going up 1 unit anymore. It is now having the interval, right? Having the interval. Then eventually we can have the interval and the interval, and then we can eventually arrive at the similar point, close point to the target height, right? Target height is beta. We may arrive very close to the target height, then we can stop, depending on our tolerance. Afterwards is bisection. So we have the possible boundary here. Then we pick the middle point, and then we pick the middle point, we pick the middle point, and so on. Then we eventually will arrive at this one. So this is the step. But the most difficult part is the implementation of this thing. Assume that this is given, g is given, then you should create a function doing this. Right? You should create a function doing this. This is the toughest part, even though it's not really very difficult in theory, but using this thing repeatedly might be tough. Right? So you should implement this. Then your program will go to this part and then calculate and then give us b. Right? So what this does is giving us b, right? And then check b, and then here check, and then reassign g, and then b. Reassign g, and then b. Reassign g, and then reassign g, and then accordingly. I will pause, and then you can check whether you follow it or not. But let's take a break anyway. Let's resume at 3 p.m. by this clock.
Do it on that. Do it like that.